All right, let's go on to the mass spectrometer here. We've kind of already talked about that. Basically, it is a way to separate atoms based on their mass. That is very useful for isotopes especially. And so the way it starts is you have the sample here. You shoot this sample out here and you give it a charge. You remove some electrons. And it passes through a magnetic field. Magnetic field will make the atoms bend. And the heavier they are, the less they bend. The lighter they are, the more they bend. And so you see here there's a separation. The lightest one bent the most, the heaviest one bent the least, and then it'll come over here and hit a detector. Okay? And so it can tell exactly how many particles hit in each spot, and then from that it can figure out the mass. Okay? And so then it will produce a graph for you. Over here in the bottom here we have mass along the horizontal axis. So this has a mass of 11 AMUs, 12 AMUs, 13, and so on. And on the vertical axis is the relative abundance. How common were they? Ranging from 0% up to 100%. And so in this particular case here, we have a series of peaks. We have a small peak at 12, a large peak at 13, a larger peak at 14, a much larger peak at 15. It's hard to see on the screen. And then a much larger peak at 16. Right? So this tells us that this particular isotope has 1, 2, 3, 4, 5 different isotopes. This particular element has 5 different isotopes, the heaviest one being 16. And so if you look on the periodic table, you'd be looking for atomic mass somewhere between 12 and 16, but closer to 16. So if you do that, it looks like it could be, I guess oxygen would be the best guess. Although it's not. This must be a made up thing here. Okay. So anyways, let's look at an example, a real example. Okay. Here we have a mass spectrum of an unknown element that has 3 different isotopes. Looking in the horizontal axis, we have atomic mass of 24, 25, and 26 here. And then you can see that 24 is the most abundant, 25 and then 26 they're both about the same. Up above here is the percentages of each one, and so almost 79% of all the atoms have a mass of 24, about 10% have a mass of 25, and 11% have a mass of 26. Right? So let's answer a couple questions about this mystery element then. The mass of the most abundant isotope, well, that's the one with the biggest peak or biggest line there, so that would be 24. And again, the unit is AMUs here. Find the atomic mass of the mystery element. Okay, we know how to do that. So you would take the mass of each isotope, we'll say 24 AMU, and multiply by its percent. I'm just going to use 0.79 for 79%. Then we're going to add to that the 25 AMU one, and that's 10%. And then the 26 AMU one, which is 11%. We're going to add those all together. Right now I can tell you that's going to be between 24 and 26 and closer to 24. So let's see what we get. I got 24.3 AMUs. Don't forget your answer box, makes the answers a lot easier to read. So then you look on the periodic table, see, which element has a mass of 24.3, and that'd be good old number 12, Mg. Right? There you go. Right. And so why is atomic mass between 24 and 25 instead of the normal average of 25? That's because it's a weighted average. So because 24 is more common, the atomic mass is skewed towards it, and so it's 24.3. Okay, next question is a question from an old AP test. And so they give you a mass spectrum here of quite a few peaks here, and it says the elements iodine and tellurium have a similar average atomic masses. In fact, they're right next to each other on the periodic table. It's one of the rare cases where the heavier element comes before the lighter element. So tellurium is number 52 with a mass of 127.6. Iodine is number 53 with a smaller mass of 126.9. Okay? So similar masses. A sample was thought to have both of the elements together in it. They ran it through mass spectrometer, resulting in this particular graph shown. All these statements are true, so it's not like a normal multiple choice question where only one is true and the rest are false, or maybe three are true and one is false. These are all true. But what the question is asking, which of these letters is the best basis for concluding the sample was pure tellurium, that there was no iodine. Right? So all these statements are true, but which one explains why there's no iodine and it's only tellurium? Right? So I'll let you read through the answers real quick and choose your favorite one. Okay, let's go through these one at a time and see which ones we can eliminate. A, tellurium forms ions with -2 charge, whereas iodine forms ions with -1 charge. That is a true statement. You can look on your periodic table. Iodine's a halogen, so it forms -1. Tellurium is in the oxygen family. It forms -2. True statement, but this is called a mass spectrum for a reason, because it has to do with mass, not charge. And so, although it's true, this does not explain what we're trying to explain here. All right, so we can cross out A because the charge doesn't matter. B, tellurium is more abundant than iodine in the universe. Again, could be a true statement. I guess it is. But that doesn't explain why there's no iodine in this particular sample. Right? So let's cross out B. C, iodine consists of only one naturally occurring isotope with 74 neutrons, whereas tellurium has more than one isotope. Okay. All right, so tellurium would have more peaks. Iodine would only have one. Let's go ahead and park that one off to the side and move on to D here. D, I has a higher first ionization energy than tellurium does. If you remember, ionization energy is the energy to remove an electron. Again, that has nothing to do with mass, so let's go ahead and cross that one out too. And hopefully our answer is C. So let's revisit C and see if that makes sense here. Right? All right, so iodine has only 74 neutrons. And so that's nice, but neutrons doesn't tell us the actual mass of the atom here. Right? To find the mass, you need neutrons and protons. So then you look at the periodic table and say, okay, iodine has 53 protons. And so if this one isotope of iodine has 74 neutrons and 53 protons, it should have a total mass of 127 AMUs. All right. We look over our mass spectra, though, and we notice that there's no peak at 127, which means that none of the atoms in the sample had a mass of 127, which means that it couldn't be iodine because that's all iodine is, right? And so, sure enough, C is our best answer, and we'll circle that one. Right? So if you chose C, way to go, way to go. All right, let's go ahead and review real quick, and then we'll be all done here. Again, 3 types of subatomic particles. You have the proton, neutron, and the electron. Location, the proton and the neutron are both in the nucleus. The electron is outside the nucleus, orbiting around doing its thing. We'll talk more about that when we get to quantum mechanics. Charges, protons +1, neutrons neutral, and then the electron is -1. Mass of a proton is 1 AMU, so is a neutron. Pretty close, and the mass of the electron is about 0. We just ignore it. Again, it's 1/1836 of an AMU, but that's close enough to 0. Occupied space of the atom, very little. Most the protons and neutrons are found in the dense nucleus, which takes up very little space. The electrons, on the other hand, that's most of your atom there. Well, most of the atom could be occupied by electrons, but it's usually empty. Right? So role then, the role of the proton is to determine your element. If you change the number of protons, you change your element. The role is also to attract electrons to itself. The neutron, if there's a job opening for a neutron, it would say that you must determine the isotope of your element, which determines the mass. Its job is also to stabilize the nucleus. There's something called the strong nuclear force that holds the nucleus together. Those only exist between the proton and neutron. If your nucleus has protons in there, and as you know, if you have 2 positive things, they're going to want to repel each other. So there has to be a stronger force than that holding them together. That stronger force is the strong nuclear force. but sometimes it needs a little bit of help. It needs a little extra strong force, and so the neutrons in there provide a little extra strong force and hold the nucleus together. As you go higher in the periodic table, you get more and more neutrons per proton. So for the lighter elements, you usually have about 1 neutron for every 1 proton. By the time you get to, say, uranium, though, you get 92 protons and 140 some neutrons. So you have about 1.5 neutrons for every proton. And lastly, the electron here, it determines your ions. And it's also responsible for bonding with other atoms, too. And we'll talk a lot more about that later in the year. To form molecules. Okay. Alrighty then. So in terms of numbers, again, your protons determine your atomic number. Your neutrons determine your mass number. Together they determine the atomic mass. And the electron determined your charge. Alright, so going back to Dalton's whole atomic model here, which of these is true and which one's false? All matter's made of atoms? Yeah, we'll go with that. We'll put a check mark next to that. As far as we know, everything that you can hold in your hand is made of atoms. Atoms are the smallest possible particle of matter. They're indivisible. That'd be a big old no now, right? Atoms are made of smaller things, and if you're familiar with the standard model in physics, there's a whole slew of other types of particles out there smaller than atoms. 3, atoms of the same element are identical to each other. Atoms of different elements are different in some way. When we do know they are different, that would be the number of protons different. But they are not identical to each other because some atoms have different number of neutrons, which means that they are different isotopes. So that part of the statement is not true. 4, atoms of different elements join together in simple ratios to form compounds. Given a compound always has the same types and numbers of atoms. We're going to go with the truth for that one too. Water, for example, is always H2O no matter where it comes from. Whether it comes from underground, even Downs water, a river, the rain, even out there in a comet in outer space, it's always going to be H2O. And lastly, atoms cannot be created or destroyed in reaction, only rearranged. Definitely only rearranged in reaction, that's true. Atoms can't be destroyed in terms of radioactive and nuclear chemistry, but we're going to ignore that. So we're going to go ahead and say that sure, that's true too. Okay, with that, that brings us to a close-in. We are all familiar with the atom, what it's made, how to measure it, how to count things inside of it, and the next lesson is on the periodic table. I'll let you look that up in the book. I think you're pretty familiar with the family names and whatnot. And then we will get started next with compounds. So thanks for listening.